This video is going to be a little shorter. We're just going to cover temperature and temperature scales and some conversions in this video. So to start out with, let's draw two bodies. This first one will be body A, and this is going to be a warmer body. Now there's going to be another body. Let's call this one body B. Now this one will be cooler. All right. Now, what we're going to do is we're going to put these things next to each other. All right, so starting out, they're separated, they're not touching. Let's put them where they're actually in contact with each other. So here's A, and now let's put B right here next to it. Now, what's going to happen is this warmer body, since it's now in contact with a cooler body, this body is going to cool off. All right, so this one gets cooler. And if we assume the volume could change here, since it's getting cooler, it's going to shrink. So the volume is going to get smaller. All right, so volume gets smaller. Now the opposite happens over here in body B. This one was originally cooler, but now that we put it next to this warmer body, we're going to have some heat transfer effects, and the temperature of block B is going to go up. So the temperature will rise. Now, if the temperature rises, that means the particles in here are wanting to expand. So that means the volume will rise. So this body will expand a little bit. Now, what went on here was a thermal interaction. Okay. Now, eventually, if you leave these two blocks alone next to each other like this long enough, eventually all these changes are going to stop. So the volumes will quit changing, and the temperatures will essentially quit changing. Now, when all those changes are done, we say we've got thermal equilibrium. Okay, and the physical property that determines thermal equilibrium is temperature. So that's what temperature is. Now, we've got our first law of thermo. This one's going to be the Zeroth Law of Thermodynamics. And this law states that when two objects are in thermal equilibrium with a third object, they are all in thermal equilibrium. All right, so basically if I added a block C here, if block A and C were in equilibrium, and B and C were in equilibrium, then by definition, all three of them are in equilibrium. All right, so that's the Zeroth Law of Thermodynamics. Just deals with thermal equilibrium. Okay, next let's go over our temperature scales. This is going to be important because we are going to use temperature in most of our examples and our problems. First scale we want to talk about is the Kelvin scale. The unit of the Kelvin scale is a capital K. This is an SI system, and the lowest possible value you can get on this scale is 0. This is known as an absolute temperature scale. So absolute temperature scales, all motion stops at 0. So you can't ever have a negative temperature on the Kelvin scale. And absolute is going to be important because when we get to our equations later on, those equations require an absolute temperature scale. Okay, so Kelvin scale is going to be important. The one in the English system is the Rankine scale. That unit is degree Rankine. Also note for Kelvin, there is no degree. Right, it's literally just a Kelvin. It's not degree Kelvin. Now for the Rankine scale, like I said, this is the English unit system. Lowest value you can get is 0, so you should not have negatives. And this again is an absolute temperature scale. All right, our temperature conversions that we're going to need, because a lot of the times you'll be given a temperature in Celsius or Fahrenheit, for example. Like I said, to use it in our equations, we need an absolute scale. Actually, let's write that down. So let's put our equations. We'll need temps and the absolute scale. Like that. Okay. So our temperature conversions. So this will help you convert from the Fahrenheit Celsius over to Kelvin Rankine, vice versa. So let's say we're given a temperature in Kelvin and we want to convert it over to degrees Rankine. So to do that, you're going to multiply 1.8 times that temperature in kelvins. And that'll give you your temperature in the Rankine scale. Now, if you're given a temperature in kelvins, you want degrees Celsius, what you need to do is take that temperature in kelvins and then subtract 273.15. Now let's go to Fahrenheit. So let's say we want Fahrenheit, and we were given a temperature in degrees Rankine. What we need to do is take that temperature in degrees Rankine, and we're going to subtract 459.67. And then last one, if we're given a temperature in Celsius, we want Fahrenheit, we're going to have 1.8 times the temperature in Celsius plus 32. All right, so those are going to be our temperature conversions. We will use these a lot throughout this course, especially these two right here. So you might want to make note of them so they're easy to find. That way you don't have to search for them later. All right, guys, thanks. See y'all next one.